Because my name is Abdul Salam. I'm an assistant professor in the Department of Computer Information Technology at Purdue University. I'm working in the area of wireless underground communications in soil. So today I'm going to present this work on the use of wireless underground communications for soil moisture measurements. That's how we can use the underground radio wave propagation to detect the permittivity and soil moisture. So the overall system development is in the area of IoT, the Internet of Things, Internet of Underground Things. In Internet of Underground Things, sensors are buried underground. So those buried underground sensors, along with radios and all the complete system, can communicate and sense all the related soil information, and can then communicate that information using those channels. So those channels can be underground to underground channel where all the communication is in the soil, or it can be one part is in underground, the radio is underground, and the other is on some moving system like centrifugal system or in the barn where they can communicate. The purpose of this development of this infrastructure is to provide a real-time decision-making system where this information can be sensed through all the rated sensors and can be communicated to the cloud where it can be used for real-time decision-making, not only by the farmers, but also other concerned authorities. So it leads to complete autonomy on the field. So in addition to the digital agriculture, there are many other applications of IoT under this underground IoT paradigm. It's also being used in infrastructure monitoring like landslide monitoring, security, border patrol, environmental monitoring, golf clubs, and the earthquake and landslide monitoring. So this figure shows the adoption of technology. So this is from USD ARMS data from 2010, although there is 2015 data is also available. So they survey the adoption of technologies in US. So there are three major takeaways from this figure. First, this blue line, this shows the increase in the adoption of overall precision ag technologies. And then the second thing, if the new technology is introduced, for example, the sensing, the crop moisture sensing technology was not there until 2005, this gray line over here. And it was immediately adopted and almost second to the yield monitoring system. Yield monitoring system is overall high. The variable rate technology, although because this has application, this research has application in variable rate irrigation systems, where the soil moisture related data can be used to schedule sensor guided irrigation management techniques. So that is quite low, this line if you see. So because I think the return on investment because of the soil moisture technique is low, there are many factors to that. Overall, the digital agriculture adoption by the US farmer is increasing. Okay. So this idea of use of the wireless underground communication in soil without the need of any sensors. So we have just radios in the soil, antennas, software-defined radios, they communicate. This is a new idea that we are testing, quite radical one, where we totally eliminate sensors. Those radios communicate in a wide spectrum. So we are working in the microwave. So by looking at we are looking at actually two factors, the path loss and the travel time of the wave. So path loss is easier to observe because we can just sense that what's the path loss. They will show the mechanism as well, as compared to the time of travel. Because time of travel you need sophisticated equipment like VNA or spectrum analyzers. But these radios, software-defined radios, these can simply detect the path loss by looking at the received signal strength only. So then we relate it to the permittivity and to the soil moisture. So as I said, there are two parameters, propagation path loss and the velocity of wave propagation. Since the soil properties, the presence of the soil moisture has an effect on the path loss and velocity. Therefore, we think that it can be related to the permittivity and soil moisture. So to show where it fits in the overall scale. So this is the spatial scale. According to the definition of the soil moisture, there are three. So this is a recent paper that just published. They said there are three components of the soil moisture: scale, sport, and extent. Extent shows the overall coverage of the whole network. This column over here, and sport shows the unit integration area. So this technique can be, so you can see that neutron probes have 15 to 40 centimeter cosmic rays from 40 to 400 cubic meter. So this approach, because right now the underground communication where both radios are underground is limited up to 50 to 60 meters. So they can communicate up to 50 to 60 meters using some of the advanced beamforming techniques. So we can use up to here sensor networks, and its range can go up to 10 kilometers with the advancement of the technologies or with one of the above ground node. And we can also use, we can also compare it with TDR sensor arrays as well, which has the 3 centimeter unit integration area, and it has the coverage of 1 to 120 meters. Okay, so the frequency that we are using is 100 to 800 megahertz. So our radios, our software-defined radios communicate in this frequency, and in this frequency range, we start from 100 and use the delta of step to increase the frequency. So that could be 1 megahertz or 2 megahertz. And then we get the path loss by subtracting the received power from the transmitter power. This is simple. As I said, that the path loss can be ascertained easily. And this path loss also includes the effect of the antenna gain, that is the transmitter antenna gain, GT over here, and GR. So both radios are transmitting. They start from the initial frequency. The path loss is detected, and from this path loss, we find the minimum frequency. For example, from 100 to 800 megahertz, the path loss, the lowest path loss, the frequency where the path loss is lowest, will depend on the soil property, soil moisture, and permittivity. So we need to find that. That would be simple, one minimal function. So we take this minimum function, and with this, in that across this whole spectrum, we have this frequency. So once we have the lowest path loss frequency, then we need to look at the F0. F0 is the resonant frequency of the antennas. So we need to compare it with the resonant. All antennas have a resonant frequency. So because we are using fixed dipole antennas in the soil, those have the resonant frequency at around 433 megahertz. So whichever the minimum frequency is, we need to relate it to the F0, which is the resonant frequency of the antenna, to get a soil factor. And once we have the soil factor, we get the wavelength in soil, as I said, because the resonant frequency is not fixed in the soil as well, so as the wavelength, because wavelength changes with the. So then with this wavelength in the air and this soil factor, by using this expression, we get the real permittivity, the real part of the permittivity. And the second method is to look at the travel time and the speed of the wave in the soil. So CS is the speed of the wave in the soil, and we look at this difference and get the real permittivity. So by looking at the lowest path loss and by looking at the travel time, we get the real permittivity, and then by using this expression, we get the soil moisture content. So this is the whole theoretical framework. So we start with the transmission of the radio waves in the soil. We look at the lowest frequency. If lowest frequency, we relate to the resonant frequency, and then from the resonant frequency, we get the real permittivity. Second method, we look at the time domain analysis. In the time domain, we get the time of the wave propagation, and then from that, we get the real permittivity. And at the end, from the real permittivity, we get the volumetric water content. Okay, so we tested it in 4 soils. So we had different type of test beds. We had in the in a greenhouse, an indoor test bed, in a field in the clay center in South Central Agriculture Lab at Nebraska, where these are the software-defined radios that we use for the communication, for the radio wave propagation. We did 10, 20, 30, and 40 centimeter depths to validate this approach. These are the soil types. We did it in silty clay loam. So SCLG, silty clay loam in the greenhouse, SL silt loam in the field, sandy indoor test bed, and silt loam indoor test bed. And these were the depths that we tested to validate this approach. These are the antenna layouts up to 40 centimeter, and four sets in each antennas. RF waveform using 2 megahertz bandwidth, so that's that delta F. And the transmitter antenna is dipole. We kept the depth to the 40 centimeter, and same. The hardware that we use is NI USRPs N210. So for each frequency, sender sends data for 1 second, and using the radio, we collect the IQ data. At each frequency, measurements are repeated 3 times, and then we did the post-processing in the MATLAB. We did the PST, the power spectrum density method, as we explained, to calculate the path loss, and this whole system was implemented in GNU Radio. GNU Radio is an open source software that can be used to do experiments with the software-defined radios, SDR. Some of the signal, the send signal was like this, and then with depth, we have the power spectrum density. So this is the send signal. You can see that the attenuation is very high in the soil, and it changes with the depth, 30 and 40 centimeter over here, these 2 lines. This is with the frequency. This is the frequency of the send signal. And here we have this, the received signal strength with the depth. This shows, this figure on the left, this shows the change in the lowest path loss frequency with change in the volumetric water content. Here you can see that lowest path loss frequency, almost in all 4 soils, shift with the increase in the soil moisture. This is also corresponding to the resonant frequency. Resonant frequency also shifts with the increase in the soil moisture. As the soil moisture is increased, we have this shift to the lower spectrum, and there is an impact of depth on this as well. Okay, so then this shows the change in the travel time with the increase in the volumetric water content. We did these measurements with the VNA, vector network analyzer, in all these 4 soils. And again, with the increase in the soil moisture, once it goes up to 58%, that's the near saturation condition that we can go up to. You can see that it's almost goes to 38 nanoseconds, as compared to just 8 nanoseconds once the volumetric water content was around 14%. And then we went up to 38%. So this is a huge travel time change in all 4 soils with change in the soil moisture. Okay, so once we have this data, then we compared it with the ground truth measurements that we did with watermark sensors and watermark data laggers. Here you can see that this approach, this is 1/1 line. So there is just, it's a very good match with the ground truth measurements. There are some differences in some soils as well. We're still looking into that what caused those differences. Then we compared it with the top model as well. So the one we did with this whole framework that we did with the empirical data that we got it with the, we compared it with the ground truth measurements that we collected from these soil sensors. This is a theoretical framework, as Professor Scott mentioned, that the top model is the standard for this. So we compared it with the top model. We have again very good match with this one. And then in the state of Kansas, there is another very popular model called the Peplinski's model. That's basically more on the dielectric spectra. But we also compared it, and it also shows not as good match, because this might be because of the different composition of the soil moisture. The error is higher, up to 20% in this case as well, once we compare the output from our model to the Peplinski's model here. And then this the time domain method, with the time domain method ER, this also shows a very good match. So overall, this approach works. At lowest, we have 3 to 4% error in measurements of the permitted and soil moisture. And at maximum, if we compare it to the Peplinski's model, there is 19 to 20% error in that. Okay, so now let's look at some of the research challenges in this area. This figure shows the communication distance, because the success of this approach depends upon the communication range, how far we can go in the soil. So this figure shows the path loss. The higher the path loss, means longer the range. And here, there are 3 channels shown actually: AG to UG, UG to AG. This black and blue line, this shows once there is one above ground component involved. Like the above ground component on the center pivotal on the one, we can go up to 200 meters in this case. Once one, either sender or transmitter is underground, the other radio is above ground. We have 200 meter range. In some cases, we have gone up to 300 and 350 meter range as well, with one lab. But this falling red line, that is completely underground. Both transmitter and receiver are underground. And we are restricted up to 15 meter over here if we are not using any advanced signal processing techniques. We are just using simple radio and sending them for transmission and reception. But if we use the beam farming, because in the soil, there is a wastage of energies to send signal in isotropic direction because their signal are going downwards. That is of no use. By using the phased array antenna, that energy can be focused towards the above ground node. And that is called the underground beamforming approach. So by using the underground beamforming approach, we can attain a distance of underground to underground communication up to 35 meters. So that is the maximum so far that we can go. So that means up to 35 meters, we can use this approach to sense the soil moisture and the permittivity. So there are some other challenges as well because both radios, radio sensors, everything is underground, and we need to have the energy. We need to have the longer battery time. Energy consumption is an issue. Integration of sensors and system in this whole I-out paradigm. So we're working on that. For that, we need more experiments, deployments, software-defined radio techniques so that we can test the system. This work is supported by NSF and Water for Food Institute. Experiments are being done at South Central Agriculture Lab, and some of the antenna design and the radio design is done at the Cyber Physical Networking Lab and Metamaterials and Nanophotonics Lab. With this, I have come to the end of my talk.
Okay, questions for Abdul?
So I'm just curious, how dry you can go to based on the new framework because I look at the figures, sounds like the lowest soil moisture content you have is about 10%. Can you go like lower than that?
Yes, definitely we can go lower than that as well. The thing is, there is an inverse relationship between the soil moisture and frequency. So if we go to the higher frequency, the soil moisture level is higher as well. But so lower. So lower soil moisture level, higher frequency, and vice versa. So this means that once the soil moisture increases and we go up to 38, 90, 39%, the frequency will shift to the lower spectrum, that lowest path frequency. And we need to see whether our radio is capable of communicating at that frequency and then detection that lower, and whether that lowest path loss falls into that range as well. Yes, of course, theoretically we can go above as well. But for the lower end, we need to see, because if we go to another problem in that is the antenna size as well. For the extreme lower frequency, you need higher size antennas. So we need to design that. Yes.
This is a really impressive talk, and appears to be a combination of frequency domain and time domain.
Yes.
It's really interesting. One of the things that we know about frequency domain measurements with probes is that soil structure can cause the electromagnetic field to interrogate different volumes of soil, preferentially volumes that have a higher water content, soak up that EMF. And I'm wondering if this might be an issue with your approach, or if your approach will actually sidestep this issue.
I think it will sidestep that, because so we are assuming that impact is inherent in the path loss. So the cumulative path loss is actually taking into account whatever is going in the soil, in compaction, soil moisture, pore space, everything. So it's in that, it shifts with that. So if any of things changes, like any of those parameters changes, the path loss will change as well, and then the output will change.
I have a question I want to sneak in here. So can you talk a little bit about the effects of soil, the bulk electrical conductivity of the soil, and how does that impact the method?
Okay, so we have not looked into that yet, how it affects. It might be, but you have any thought about that it could?
Well, I mean, I think it will have an effect, definitely. And I think with your approach, you can potentially be sensing the bulk electrical conductivity as well, and not only the permittivity. So I think there's a real in my ignorant view, it looks like there's a real opportunity there.
Okay, yeah, that's an interesting idea. Yes.
So the lowest path loss frequency said it was decreasing with increasing water content?
Yes.
So is that filtering the high frequencies as you add more water? Is that the mechanism here, or what?
Yes, because so that's because of the complex permittivity of the soil. So in over-the-air radio communication, we have just normal diffusion, attenuation, refraction from the building, those phenomena. But because once we operate in the soil, because of the complex permittivity, there is an additional component of the permittivity, the imaginary part of that. So once wave propagates, the water holding capacity, the water holding capability of the soil actually absorb those waves. That's why in sandy soil, that frequency is high. So we don't go to that 50, 100. We never, in sandy soil, we never cross the lower threshold of 100 megahertz because of the low water holding capacity. So yes.
So how different were the four soils in terms of the texture?
Totally different. So two are more on the clay side, one was the sandy. Yeah.
Okay, over there.
Can you talk a little bit about the sensing volume, and does that change from one measurement type to another? Can you back out what that, how much the signal is being, what that volume is that?
Yeah, so being on the coverage side, the second column, so we can go up to 35, 40 meters. The attenuation per unit per meter is around more than 5 dB, between 5 to 10 dB per meter with the normal signal processing techniques. So it's mean if you are putting in a power of more than 100 dBm in the system as a transmission power, you can go up to 20 meters because of this attenuation, like this standard. It depends on the soil as well. In sandy soil, it's this lower, this number is lower, and in clear soil, it's higher. So roughly 5 to 6 dB per meter. So it depends upon your budget, the transmission budget as well. So if you can increase the budget, because we don't have this, because the device is underground, energy consumption issues are there, we cannot increase the transmission power. We need to conserve the power. We need to put the system into duty cycle. But that's another limiting factor.
Okay, last question right over here.
Can you distinguish the different project from the methods?
Yes. Okay. So the what happened is actually the depth closer to the soil air interface has like refraction effect from the soil interface itself actually on the antenna, which generated additional current on that. So based on that, once we go deeper, the impact of that refraction from the soil interface decreases because it's going up, signal is going up, it's reflecting back, it's transmitting in the soil. So through that, we can distinguish that. Yes, it's a separate work. We have done that. We have published a paper in IEEE transactions on antennas and propagation, where we have shown that how depth impacts that.
All right, Abdul, thanks. This is great. Definitely fits under the category of new frontiers in the